Well, here we are once again. It's the physics video lecture. Psci 168, video lecture 20. And look, we're going to start something new. I have some demo objects because I had said we're going to move on into thermal physics. But before we get there, we'll do a little bit of review. Namely, everything we've done up to now in physics is referred to as mechanics. Okay, so let's just list the basics that we've now learned, because things are supposed to be, if not easy, at least simple. So the simplicity in physics so far was that everything was expressed just in terms of lengths and masses and times, okay? And we had the kilogram for mass, we had the meter for length, and we had the second for time. And we knew how to get ourselves a meter. We knew how to get a kilogram because 1 liter of water has a mass of a kilogram. And a second, we learned how to make a pendulum so we could, we have access to all of these things on a pretty basic level. All of our formulas, all of our concepts were built up out of these things. So what did we have? Work, which is force times displacement. If we go into here a little deeper, we remember that was a Newton times a meter, but then Newton's law, force is mass times acceleration, means we had kilograms times meters per second squared, mass times acceleration times meters again. So it was mass length squared times squared. So power would be work divided by time. We'd have another second in the denominator, and so forth. So everything so far built up out of these quantities, and we call that mechanics. Okay. So the science of mechanics, and I should mention a couple more things. Motion, right? Meters per second. Acceleration, meters per second squared. So far everything, mass, length, and time. Okay. And that is referred to as mechanics. Science of motion, science of motion is kinematics, forces in motion is dynamics, the whole thing is classical mechanics. Okay, so what, let's even go ahead and draw our little cartoon, hydropower cartoon with the mountains in the background. We have the two levels of water. We've got the water up here, we've got the water down here. We have the sun's radiant energy evaporating water so that we have the water cycle. Okay, just to remind you, all those things are part of the entire energy picture, but we've mentioned the sun's radiant energy. That's going to be thermal physics as well, but otherwise everything we've talked about has been in terms of mechanics. So I'll just put this note here. We've got sunlight, evaporation of water, etc., the water cycle. So that's one place where there's going to be thermal physics. Another place is going to be where there are power plants that burn something. So we have to study thermal physics. And the other cartoon, we have a power plant in the background, that kind of thing. Of course, we had electricity, that's going to come up later as well. But our next topic is thermal physics. And the interesting thing in terms of this introduction, once we get through some preliminaries, it's actually all going to reduce to mechanics again, And once it reduces to mechanics, you know, this is our energy concept, right? Work. So good, let's get started with thermal physics. And we'll just begin with the sensation of hot and cold. We're going to build it up. We're going to build it up from the most basic concepts and ideas and sensations, and then we'll try to eventually will make contact with these concepts and tie it all together. Good. So I'll begin. I'm about to light a torch here. Ignite a torch. And I will begin with, once again, I'll just write thermal physics here. That's our topic. And we'll begin literally with the sensations of hot and cold that we can feel on our skin. So first of all, sensation of hot, sensation, hot, and cold. And the sensations of heat and cold are associated with something. So for example, I would have, didn't bring any ice today, but I did bring the torch. I'm going to use it. There we go, we've got a torch, and it's real. It won't burn me. Okay, careful what you do here. So that's the fire part. And I didn't bring a bucket of ice, but I could have, and you know, I'd have a bucket of ice. Put my hand in ice water, that's cold, and I can put my hand close to the flame, and that's hot. Okay. So that's what we're talking about with the sensation of hot and cold. And then I'll just line these things up here. Fire and ice or cold water or something, take your pick. So that's the second point. We've got the sensation, we've got what it's associated with. And my third point is going to be a related phenomenon. A phenomenon related to these heat, hot, and cold things. So what I'm going to do is heat up. I have to pick out the right objects here. This is always a fun demonstration. That looks like a pear, and let's pick the right ones here. Good. So here we have two sets of balls and rings, and they're made of brass, and here the ball will not quite pass through the ring. So I'm going to heat it up and see what happens. Okay. So this takes a moment. Gotta have a little bit of patience here. But this is a real flame, so we should get some result here. Well, I can't see any difference here. It was a pretty close fit. There you go. I'm actually able to just pass this through. So what phenomenon am I talking about? I'm talking about what's thermal expansion. Okay, I'll write it down in a moment. So thermal expansion is when you heat something up and it expands. And like I said, you wouldn't even be able to measure this on a normal ruler, but it expanded on a ruler. It probably expanded by 1/10 of a millimeter, okay? But that was enough for this to pass through. It's also an interesting situation, and this happens sometimes. If you leave this here and let it cool off, which I'm not going to do, it will actually grab this thing so tightly that you can no longer pull it off. And you have a little problem getting it off with heat, because then both objects expand, okay? So thermal expansion, let me go ahead and put that down here. It's a really important one. Thermal expansion. So that was a demonstration. Now, this related set here, also very close. There's a slight gap, but the ball does pass through the ring. If I heat the ball up, it will also expand. So let's do this, give this a try. Now this is more massive, right? It's not so thin, and it takes a little more time to soak up enough heat. We'll give it a couple more seconds. But the flame is pretty hot, so it shouldn't take too long. Right. There you go. In fact, it will no longer pass through. Expanded pretty nicely, okay? So thermal expansion, very important. Now here is another example, but first I'm just gonna heat this. It's just a metal, I notice it has two different colors, but it's a thin piece of metal. Bends rather nicely, okay, under extreme heat. And the explanation of this is that even though this is a thin piece of metal, it's actually a sandwich of two different metals, and the two different metals have different thermal expansion properties. So if one of them expands more than the other when it's heated, it pushes the whole thing over in that direction, okay? It's called a bimetallic strip. So let's see, let's go ahead and collect these results. So we had the ball in the ring, just so you, and 0.3 here, this will be 0.1. We had the bimetallic strip. This one we want to stay with for a moment. So if I draw a kind of a large scale version of this, it is two very thin different pieces of metal, and then when we applied heat to it, we actually had it bend. Now I put that scale up there, and you guys make a nicer picture. The reason I put a scale here is because we already have a thermometer. What we could do is we could say when it's pointing, when it's straight, we could say that's room temperature. When it bends over here, it's very hot. I can show you later this semester that if I dip it into liquid nitrogen, which is very, very cold, it will actually bend in the opposite direction, okay? So this already gives us a thermometer. So thermometer. And in fact, let's start a new topic here. So the thermometer, this is already an example of a thermometer, but it has three settings, right? Very cold, room temperature, and very hot. So what we have to do next is invent temperature scales. So thermometers, and the next point, temperature scales. So temperature scales, we would have to have some gradations in here. And once we have these, we can then go back to our sensations and be more objective about them. But yeah, here we are with the temperature scales that we still have to develop. So another example of a thermometer, here I'll take this out, would be, of course I'm not even going to hold this close to the camera, but this is a little capillary with some fluid in the bottom, in the red reservoir in the bottom, and then there's a scale. Maybe I will hold this up to the camera. that going to come in focus? Doesn't want to. Let's try something else here. Maybe if I hold it up against a book, camera will be fooled. There we go, there's a temperature scale. Okay, there's a reservoir at the bottom, thin capillary, and if you go up high enough, it's reading 22 degrees or so, isn't it? Okay. Okay, that was pretty low tech. Now, so yeah, I have a thermometer, and what I could do is put it in a bucket like this with ice and water. And then I could put it in a, not plastic, but I could boil some water, and then I would have boiling water, same thermometer, and even under body temperature, if I hold this in my hands, the column rises a bit. So that will lead to our next drawing for thermometers and temperature scales. Thermometers and temperature scales, we're continuing thought right there. So suppose we have this capillary, and there's a reservoir at the bottom, and I'm going to draw a second one, like what I just showed you. We'll even put the red fluid inside since we can. It's going to go up to here. So what are we looking at? We could say that this one is where water or ice melts. Okay, so ice melts here, and up at this one up here, we could say water boils. And then depending on which temperature scale, we could assign different numbers for these. So we have the, here, I'll go ahead and put that right there. Maybe this one's got to be a little taller too. Okay. Okay. So we've got ice melting and water boiling, and we just assign this a number 0 degrees Celsius and 100 degrees Celsius. And on the Fahrenheit scale, we would have 32 degrees Fahrenheit and 212 degrees Fahrenheit. And then we would make an even scale for these, and we would make a scale for those. And that's how you make a temperature scale. You need a uniform device, and you just need a couple of reference points, and then you make up a number. Okay, you can see this is actually arbitrary, 0 and 100, 32 and 212. Okay, because what we have here is a physical phenomenon, and of course this goes well with our fire and ice. This is going to be a little painful to put your hand in. This is going to be a lot more painful, but there's the hot and there's the cold. So this brings us back to the sensation, but we now have a whole scale in between here. So maybe the only thing to do about this is to assign a couple of numbers for you guys to figure out and look up. Of course, you can always just type this into a machine at this point, but go ahead and find let's see, body temperature, room temperature, in degrees Celsius. Okay. And room temperature, well, that depends on your preference, right? But still, it'll be good for you to know how many degrees Celsius certain room temperature is and what your body temperature is. Now, of course, you can just type these into a search or into a computer and get the answer, but I will derive the conversion for you guys because it's kind of interesting. So, temperature conversion is what we'll call this. Temperature conversion, and we can actually just use these 4 data points in the following way. So let's say this is the degrees Celsius axis, and this is the degrees Fahrenheit axis, and we've got these 2 uniform devices. They're really the same device with a different scale drawn on them. So what do we have here? We have 0 Celsius and 100 degrees Celsius, and we have 32 Fahrenheit and 212 Fahrenheit. So just to make this somewhat reasonable, so here we have 32 and here we have 212 in the Fahrenheit, and we're just going to draw a straight line there. Well, oops, let's make that line a little straighter. 32, 212. Okay. And we have the Celsius scale here and the Fahrenheit scale there. So what is the slope of this line? You know, the rise over the run. So it's 212 minus 32, which is 180. Degrees Fahrenheit divided by 100 degrees Celsius. Okay. So the equation of this line, which is going to be our conversion line, is going to be the degrees Fahrenheit is equal to 32 plus 180 over 100, that's 18 over 10, that's 9 over 5, plus 9/5 times the degrees Celsius. So let's do it this way. This is better. T, so degrees Fahrenheit is 32 plus 9/5 times T degrees Celsius. And I can actually continue this. I can solve for T degrees Celsius is equal to 5/9 times T degrees Fahrenheit minus 32. So those are your actual conversion formulas. Good. So yeah, it could be for formulas, but when you're looking these up or any ones you want, for example, cooking temperatures you might want to know about as well. But definitely body temperature and room temperature, degrees Celsius. You can go this way using the second formula, or you can type it in somewhere, whatever works. And yeah, just leave room in your notes and you get these. I'll just write others. If you're interested, now's the time to find them and just make a little chart. Okay, so those are our temperature scales and conversions. And I'm going to consult the clock here. So next I want to introduce this device right here. What is this? Kind of as a mock-up, put the thermometer in here. This is just a beaker of air, or it could be some other gas. And it's connected by a tube to this bulb with the red fluid, goes up this tube here. This is open to the atmosphere here. This is open. And I'm going to show that this is actually a thermometer. I could just hold this, but it takes a little while to warm it, but not that long. If you look closely there, you see the red water is moving up the tube. So I'm heating this glass, but there's air inside. It's the air that's being heated. And yeah, I don't think it's going to go much more, so maybe we could say there's body temperature right there. Some approximation to it. Say I want to get it to go a little higher. A torch. So that's hotter. But yeah, this is clearly a thermometer, and it's called a gas thermometer. Now this demo object gets used for other things as well, so it is demonstrating the principle of the gas thermometer. Let me put this in here. And I'm going to draw a slightly different version of it, but you've definitely seen what's going on. You can imagine I have boiling water in a beaker, obviously not plastic, and I know it's 100 degrees, so I could use the boiling water to set the 100-degree mark on this thermometer. But so it's 100 degrees because it's boiling water, and then that would go up to some certain point, and I'd say that's my 100 degrees. I could do the same thing with ice water, and I'd say that's 0 degrees, and I would give a different point for the 0 degrees. So that's the concept I'm going to draw on the board for you. There's a little more to it than that I'll discuss as we're constructing our drawing. So good, we've got these thermometers. We have our temperature scales now. Good, temperature conversions. So this next topic is called gas thermometer. The gas thermometer, more specifically, the constant volume gas thermometer. So, gas thermometer. And here, parenthetically, constant volume. I'll explain that. So we have to draw a generalization, a slightly different version of this, but roughly this. So what we'll have here is our beaker, and we'll say we have a glass bulb in there. It's going to go over to here. But yeah, the beaker has water in it. Some source of heat, or it could be cold water. And it's hooked, it is connected to a larger vessel here. So this is represented by this right here, and this larger vessel representing that. We're going to have a flexible hose come out of it, and then a column here. And this column, this tube, is open to the atmosphere. Open to the atmosphere. Okay, so in honor of the red fluid there, go ahead and have red fluid here. Okay. And this red fluid goes all the way up, say, to here. Now the reason this is flexible, this is kind of subtle, flexible to allow constant volume. So if you're doing a measurement with this device, when I say constant volume, I'm requiring this level to remain constant. Okay. This level here remains constant, and as the gas pressure pushes this down and up, we adjust the height here, so that's constant. And this column here, we're going to call H, and that measures the pressure. Measures the pressure. So yeah, the column here was also measuring the pressure. The pressure where? Right in here. So let's go ahead and make our gas. Well, we're going to make our gas molecules. So there's gas in here. We'll just make those little dots. Okay. And we'll have the water in here. There we go. Some color going on. Okay. So how does this thing work? Oh, one more thing. We have to have a thermometer. And I'll just go like that. We have a thermometer measuring the temperature over here in degrees Celsius. We have connection with gas to here. If we increase the temperature, we increase the pressure apparently, because this column increases. Okay, so this pressure is being measured proportional to the temperature. Okay. So we have gas molecules. Okay. Or otherwise, we're just going to say gas molecules. Measures the pressure, and over here we're measuring the temperature. Okay. So we have to do a lot of work with one of these. Take a lot of data, maybe get some of the grad student to do the data, the experiment. So what we're going to draw here, and we'll end with this. I better consult the clock again. Yeah, perfect. So what we're making here is the graph of pressure versus temperature. And this graph of pressure versus temperature is with this constant volume gas thermometer. Okay, so this is a graph that gives the results of these experiments. And the thing is, when I have, say, gas molecules in here, we can exchange the gases. We can just have air, that's the easiest one to use, but we could evacuate this side and put in a different gas, maybe helium, hydrogen, carbon dioxide, different gases, and then we would heat them up, cool them, measure the pressures with the height of the column. Good, so what does this graph look like? Leave a lot of room on the left side of your graph. This one should be fairly big. Okay, so here's the temperature in degrees Celsius. Here's the pressure. I'll just write pressure. Doesn't matter the units. Atmospheres. Okay, here's 0 degrees Celsius, and here's 100 degrees Celsius. Well, the pressure increases, the height of that column increases with temperature, so you've got a graph that has a slope, okay? And this is gas A. Then you do a different gas, I'll do a different color here. And you also get still straight line, pressure versus temperature. The extrapolation of these is very interesting. If you extrapolate them, you know what? Let me just draw them now that I've kind of discussed how this happens. So the extrapolation, that, and the same extrapolation. Okay. So these were your data, this is your extrapolation. So, very interesting thing happens. You've got this linear, right, straight line behavior here. If you extrapolate them, they all extrapolate to the same point. And that point happens to be minus 273 degrees Celsius. So that indicates there is a fundamental temperature scale that starts here. And what we do is call that absolute zero. And we say we have an absolute temperature scale. It's called the Kelvin temperature scale. Absolute zero equals 0 Kelvin. So you'll notice the Kelvin scale is using the Celsius degrees. It's just been shifted by 273 degrees. So 100 degrees Celsius would be 373 Kelvin. Okay. So we're adding this to our temperature scale. The importance of this one is, we can say this is the physicist's temperature scale. The significance of absolute zero is that it corresponds to zero motion whatsoever. So if we have atoms moving around at 0 Kelvin, they have stopped moving around. Okay. So absolute zero is a very important fundamental temperature here. By the way, we can add this to our temperature conversions. You can put it back in those notes as well. We would write temperature in Kelvin is equal to temperature in degrees Celsius plus 273. For some reason, they decided not to put the little zero there for degrees, but it's just temperature in Kelvin, capital K. So let's put that as a note, because we can wrap things up with that. Note 0 Kelvin is the coldest possible temperature. There is no negative anything in Kelvin, because that's where everything just freezes and there's no motion whatsoever. So 0 Kelvin is lowest possible temperature. Back with the Fahrenheit and Celsius scales, there's no idea how negative the degrees can get. But it's this concept here and related work as well that proves that the lowest possible temperature is 0 Kelvin. And that's where we'll leave it for now. We have a lot of thermal physics to do, but see you next time.